What's up everyone? Today I'm going to be talking to some rocket experts about how dynamics concepts relate to how rockets actually work. My first question is, how do these huge, heavy rocket ships even get off the ground?
That's a great question. As we know, rockets are super heavy, with the average one being around 5 million pounds. And of that 5 million pounds, around 40% of it is the rocket fuel itself. So that raises your question, how do we actually get that off the ground? Well, this is what thrust is for. Thrust is the burning of the rocket fuel, and it creates a downward force that pushes the rocket itself up. The force from the thrust must outweigh the force from gravity on the rocket, meaning that its net acceleration, according to Newton's second law, would be upwards.
With that much weight being fuel, as it gets used up, does that affect the rocket's acceleration?
As the rocket launches, the weight starts to drop drastically. About 2.26 million kilograms of fuel is burned in about 8 minutes. Since our mass is changing, we cannot use our F equals ma equation. Instead, to find acceleration at different points during the flight time, we'd first have to have our exhaust velocity, which is the amount of fuel, how fast it's coming out of the thrusters, over the total mass of the rocket at that point, multiplied by the mass of the fuel, multiplied by the change in mass over the change in time.
Okay, so it's accelerating constantly through its whole course.
No, so thrust usage is actually a thrust curve. It's mainly dependent on three things. What Keith already talked about was the change in mass. Now it's also dependent on the atmospheric changes and the change in throttle. Talking about the atmospheric changes, as altitude increases, we can see the ambient pressure decrease as it goes higher. We can see throttle management. At ground level, it's a large amount and acceleration and velocity is increasing. Once we reach a value known as max Q, which is the maximum aerodynamic pressure, there's a lot of pressure on the outside of the rocket ship, which can cause problems. So we do something called throttling down. This decreases the throttle and acceleration while the velocity is still increasing to lower the outside pressure on that rocket ship.
Oh, interesting. So it's just going straight up.
Initially, the rocket flies near vertical. This is so that it can quickly escape the most gravitationally dense part of the atmosphere, reducing the amount of fuel consumed. Once the rocket gains altitude, it begins to gradually tilt. This is called a gravity turn. This movement gives the rocket's path its part elliptical shape. It's caused by the mixing of Earth's gravity with the horizontal motion of the rocket.
Alongside that, lift is also extremely dependent on launch angle and trajectory, where if a rocket is at a straight vertical angle, there's little to no lift. But if it's launched at a slight angle, and as the trajectory goes has a slight angle, lift helps push the rocket up.
So what is orbital velocity, and how does something stay in orbit?
Orbital velocity is the speed needed for an object to stay in orbit. For low Earth orbit, this speed is around 7.8 kilometers a second. In dynamics, we learned about general circular motion and nt coordinates. We know that when our velocity tangent to the path is constant, it means the only acceleration acting on the body is your acceleration normal to the path, or your centrifugal acceleration. This is exactly what happens when something orbits. The previously mentioned 7.8 kilometers a second is your constant velocity tangent to the path. That means that the only acceleration acting on the body is normal to the path, caused by Earth's gravity. So basically, nt coordinates and general circular motion are the roots of how something orbits and stays in orbit.
So what forces are actually acting on the rocket?
The center of pressure includes all the aerodynamic forces that act on it. This includes drag, lift, and normal forces. The center of pressure is directly related to the stability of the rocket or if it deviates from its flight path. The center of pressure needs to be below the center of gravity in order for the rocket to stay stable. Drag, on the other hand, is directly related to the opposing forces on the rocket. On takeoff, the rocket is running into many air particles which resist its motion. The more the rocket speeds up, the more particles it hits, which increases the opposing forces or drag.
Oh yeah, I just saw the Artemis 2 launch. Why did it do a circle around the Earth?
The arc around the Earth may seem like a waste of fuel because of all of the extra distance traveled, but using natural forces like gravity is what enables rockets to change direction and is necessary for every flight that goes into orbit. The process of using a gravity assist is so useful because it borrows momentum from a huge source like the Earth or Moon to drastically change the velocity of something small like a rocket ship instead of using fuel. It works by entering a planet's gravity at a specific velocity and radius that allows the ship to go around the backside and leave with the exact same velocity relative to the planet that it entered with.
Wow, that's some pretty cool stuff. Who knew dynamics was so applicable in real life situations?